Okay? Now we're going to look at number 12. If you fill the blanks in, then I'll come back and tell you about it. I'll explain what I'm saying, just get the blanks filled in without trying to comprehend. Who Jennifer? I'm walking y'all here. You ain't got to sign in, got over here. You Jennifer, right?
Melissa Simpson.
Oh, you're Melissa, I'm sorry. You're Melissa Simpson. So Jennifer Whitney is still not here. Okay. Let me explain what this is all about. There's two words that's important to biochemistry and anything else. One's called hydrophilic. What do they do first? Hydrophilic first. One's called hydrophobic. Okay. If you will dissolve in water, we call you hydrophilic. Salt is hydrophilic. Sugar is hydrophilic. If you will not dissolve in water, we call you hydrophobic. Chewing gum, hydrophobic. Fat, hydrophobic. One dissolve in water. Now, that's a good thing though, because see, if I want to keep water out of cells, then I'll make that cell membrane made of fat. And water can't go through fat. The fat won't let it. Fat won't dissolve in water. So if you won't dissolve water, then water can't go through you. And if you think you need a fat-free diet, you got to think again, because you have fat in your cells on purpose. So your cells don't absorb water from the environment around them. You stand in a tub, you don't swell up like a piece of bread would, because your fat-containing cell membranes keep that water out of your cells. But then the problem becomes, well, if you want some water in your cells, how do you get water inside? You got little pores open and closed. And those pores let water go in and stop water. But the fact that your cell membranes are full of fat, they're called phospholipids, that makes sure water cannot get into your cell. If you look at leaves on trees, that wax you see on, that's a waxy product, but on days like today when it's real hot, that keeps the water in those leaves so they don't dry out and wilt on you. So if you don't water your plants, they're going to wilt. But the wax does make the plant last longer with your non-care. My wife buys a plant, she doesn't get her water. And a month later, she finds a plant dead in her hammer. Outside my door, I have my plants, I water them. I see them all the time. And I say, how do you put your plant when you see it? You'll see it wilting, and she never does. So I buy her silk plant. She can't kill a silk plant. I don't know, maybe she could. But usually you can't. But silk plants don't freshen the air like a real plant does. Now, so one more time. Water is a covalent bonded thing, because if you look at, and I may have one, if you look at a water molecule, it's like Mickey Mouse, circle with two little ears on it. It ain't like your ears over here, they're on top of it. I mean, here's a circle, and here's the two H's. So a lot of folks think it's a circle, H and H. It's not. It's a circle with H up here. There's the oxygen. The H's are not equal across from it. They're on top of it. That makes water a polar covalently bonded molecule. That forms like a wedge. It can get in places and separate. like if you put salt in water to make salt water, the salt gets in, the water gets in there and separates sodium from chlorine, and you're right back to having the two properties inside. Now, if you take and let the water evaporate away, when the water's all gone, fill inside there, you got your salt back. Because when water evaporates, it don't take the salt with it, and as the water leaves, the salt remains behind. Alrighty, so basically the polar covalent bonds with the title of the slide, that's what causes some things to be hydrophobic. If you have a phobia, what's that mean?
Afraid?
A fear, a dislike. So hydrophobic things don't like water because they can't dissolve in it. Hydrophilic things love water because they dissolve right in it. They become part of the water. So hydrophobic substances do not dissolve in water. They do not like water. So keep that in your mind as you keep these things straight. Because all through science, that's the beauty, because when fat is used, they're using these hydrophilic properties to keep water either inside something or outside something, like the wax on a leaf. Well, that keeps water inside, but it can't get past the wax. And when you water your plants, that leaf don't dissolve that water. The water falls to the ground. So if you're going to water a plant, you water the ground, or the water comes up to the roots, goes out to the leaves. All right. This is how water looks. And you see, I try to show you there's a lot more electrons around the O than around the H's. When you got more electrons, what's your charge going to be? That's that negative charge up there. And then at the bottom part, where the two H's are, there are not many electrons. That's where your positive charge is. Now, if this is positive, what part of that water is going to be attracted to it? The negative part or the positive part?
The negative part. Negative part.
The negative. If this is negative, then which part is going to be attracted to it?
Positive.
That's the beauty of water. Because it's polar covalent, it can be attracted to either a negative thing from the positive end or a positive thing from the negative end. There are not many things like that. Water is a unique substance. I mean, we drink it and don't think anything about it. Water is perfect for what it's supposed to do. And we go out to space and look on Mars and look on Jupiter. If you can't find any water, then you forget it. Life won't be there. As far as we know, there are no living things that can live. Question, can some living things live without oxygen? Yeah. There are some living things that actually oxygen will kill them. They better have no oxygen. That's called anaerobic. But all things need water, even the anaerobic things. So the idea of, I need oxygen, but there's some bacteria you'll kill with oxygen because they can't live with it. I can't live without it. You can't either. But right there is a picture of how the molecule looks, and you'll see there's all the little red dots. Those are electrons. And they're all there around that oxygen molecule. And that gives you kind of a negative charge. And the positive discharge is on the bottom of it. All right? That's another picture of the polar covalent. Fluorine's a hog. It won't share equally with hydrogen. And when you don't share equally, that means you're polar. You're different. If you're non-polar, you share equally. You're the same. And in that case, that's your hydrofluorine type of a substance. It's just showing you though that that's also a polar covalent compound. One side is negative-ish, one side is positive-ish. Actually, there's more than one kind. All right. But if you had two H's, they'd be the same size. That would be a non-polar. If you had two O's, that'd be the same size. That'd be a non-polar. But H and O, like you saw previously, one side's going to be swollen real big, one side's real small, and that's polar. Polar means there's differences in size. if I am for something, and you're polar opposed, then you're against it. If our opinions are polar apart, then I say yes, you say no. I say up, you say down. That's what polar means. If we're non-polar, I say up, you say up too. And a lot of marriages are polar. I don't need two of these. My wife makes a perfect offset to me. We should be polar. Hydrogen bonds are very, very, very important. Go ahead and get your blanks to it, and then we'll come back and talk about it. I'm going to look ahead for a minute. I'll be right back. Okay, wrong way. Yeah, I can say something here. I don't want to spill my beans too soon. Hope I got a picture coming up of this.
You need to put a 2 after attractor.
Huh?
You need to put 2, the word 2 after attractor.
Is attracted to the, thank you. Is attracted to. Looks fine now. Obviously, I don't plagiarize. These are my own words. Somebody thinking so fast to leave words out, which is a problem I always have. Now, let me explain what this means. You ever hear of water dripping from your faucet? Drip, drip. You ever seen it actually form the water drip? How the water gets a little bigger and a little bigger? Forms that little shape like this, and all of a sudden it's so heavy it falls. What keeps it stuck up there until it falls?
Covalent bonds.
Huh?
Covalent bonds.
Right there, it does. If I go back a moment, that's water, right? If I had 2 of them on there, this end is positive, right? If I had another one, would it be H to H or O to H right here if I had another one? It'd be O to H because this positive would attract to the negative end. But that's the attraction. They hold themselves. Now, so what happens as that water drop forms, it bulges down a little heavier. They don't want to fall because they're bonded. The H portion of one water molecule is sticking to the O portion of a molecule next to it. So what makes it finally fall? What makes it finally fall off your faucet and hit the sink?
Gravity. It's too heavy.
It's purely gravity. When that drop of water gets so heavy that it overcomes that bond, it'll fall. If you take a straw and you have a Coke, if that wasn't true, would water come out of the straw? Would Coke? No. That's why when you suck on a straw, the Coke, the water, whatever it is, will actually climb that. If that was like in powder, it wouldn't do it.
So powder wouldn't go in the straw to suck on?
Huh?
So
Powder won't clean like that. Powder pours, it don't drip like that does. But water, that nature of water is why even a tree is called transpiration. When you water the ground, the water goes in, right? The roots take it up. The water at the leaves is evaporating. It's evaporating through stomata, which is actually made for it. As water leaves, that forms a pull. And it's sucking water up from the ground and it goes up the tree. So transpiration, that's why you don't water the leaf. You water the ground. Because that's where the plant's getting the water from, the ground. But because of the way, that's right there, that's just one water molecule, that's just one of them. But the way they're designed, a positive end, they're going to stick to a negative end, and they're going to make one big conglomeration. And when the water finally drops, it's because gravity is pulling so hard that the little hydrogen bonds no longer sustain it, and it falls off and drip, drives some folks nuts. Now, electrostatic is the word I'm looking for. What is static electricity? Static electricity. What's a prime example in nature of static electricity?
Lightning.
Lightning. When a warm air mass rubs on a cool air mass, let me rub my hands. Electrons are given off. And when the charge difference is strong enough, it'll come to the, not the ground, to the highest point on the ground, could be your head, could be a tree you're under. Some lightning goes from the ground up. Do you know that? It goes both directions. Usually, it's the clouds rubbing together so the lightning comes down to the earth. And can lightning also happen on a clear, cloudless day?
Yeah.
Yeah. It takes air masses. Summer lightning a lot of times happens, you go, this is weird, there's no cloud in the sky. I see lightning bolts happening. But usually, as you know, lightning accompanies a storm. But yes, there's turbulence in the air, and that stuff is moving around. You don't be by a metal fence, do you?
No.
All yours are lightning rod. The tallest thing around, electricity takes the shortest route. And if you're standing there, then the shorter route is from here to your head, as opposed to here to the ground. Now, if you're under a tree during a rainstorm, you're just plain stupid. As you well know, probably. Now, does a 5-year-old know that? That's what you got to teach him. Son, don't get on that tree there. I'll get wet, but at least you're alive. They want to, and there's old folks who do that too. Why doesn't your car get struck by lightning? You're in your car, sitting there, lightning popping all around, and the best place you can be, you know what?
Because the
Your rubber
tires.
tires. Your rubber tires do what for you? They ground you. If you're working electricity here, and you have the rubber handle of the screwdriver, even if you hit live juice, it won't get you. But what are you doing this way? Your hands on the metal part as you spin a screwdriver.
You're screwed.
Guess what's going to be nailed? The hand is, you defeated the idea of the rubber, so you wear gloves. You look at these folks, the Georgia Power people, big old thick gloves on. That kind of stuff, flat out. I've always been scared of electricity. I respect it. And I've been bitten by it before. I don't want to get bitten by it again. Yes, sir.
You know what electricity looks like?
Like blue.
I was asking about.
You ever smelt it? You ever smelled electricity?
Yeah.
Yeah.
Yeah. I associate the smell more than anything else. And also, for I was like a hunter a whole lot. And before a storm, deer move. So if you can be out there in your tree,
Or right after.
or right after, here you are, you have a metal deer stand, you're holding a rifle and you got metal, you got the bow and arrow. My hair will start to tingle before lightning strikes. I can walk by a TV set, and my hair will be pulled toward it. If I'm in a tree and my hair starts tingling, I come right down right away. So next thing, you ever had lightning strike next to you, near you?
Yeah.
The sound is, I can't describe, the sound is true. I've heard artillery rounds go off, nothing like lightning. Lightning is the most violent thing I've ever heard in my life. And if it strikes like a tree right next door to you, you're going to be amazed at the violence. Things vibrate, it's just terrible. But static, if you take your comb your hair a whole lot, you're rubbing electrons from your hair onto your comb, making that comb negative. you bring it by a sliver of paper, the electrons force those electrons away, then the positive part of the paper will stick to your cone. You know it, right? Now, it'll soon fall off one. But when the electrons finally make their passage over, everything equalizes, now there's no different charge, the paper falls off. So that's electrostatic. You can walk on your carpet. Touch your doorknob. Feels that little spark. Touch your dog's nose. And usually I'll walk by and just touch my shoulder. Just a love tap. Boy, if you shock her, she is mad. These things I do on purpose. And I don't do it on purpose. She'll do me the same way and it's going to be all right. When I do her, she gets all bent out of shape. You think I'm amusing her. But no, baby, that's a love spot. All right? So anyway, that hydrogen bond is that electrostatic attraction we're talking about. The negative of the oxygen part of the water being drawn to the positive, the hydrogen part, that's your electrostatic attraction. And that's why water molecules stick together.
And then
Can you fill a cup to the water even over the brim?
Yes.
That's because of the, otherwise it would just flow over and fall, wouldn't it? But water's, try with alcohol. See if it'll bulge over. I don't drink. But see if alcohol will do that, bulge over the rim. I know water will.
So you're saying that
Maybe like a beer? Is that what
Yeah.
you're saying that it'll continue to hold together because of the electrostatic
That's
attraction.
exactly what I'm saying.
Eventually, the gravity will take over.
We'll pull it apart, right? But you can take a cup of water with a dropper and drop. It's even above the rim and keep dropping into it. It'll finally overflow. It takes a long time for it to do it. It takes a long time. I've never tried that with like alcohol, like rubbing alcohol. I've never even tried that. I don't know if it will or not. I know water will, but one day I might try to see if I can take that dropper with alcohol and make it go above the rim. I don't think it will, really. I think it'll flow right out. That's just me. But then again, if you were so inclined, could you suck the alcohol up a straw? I wouldn't want to, but could you? If you could, that would be some electric. So I don't know how far you can stack alcohol above the rim. I know water go way above the rim. It'll go way above the rim before finally one more drop does it because of the attraction. All right. More about these bonds. We know that water sticks to water because of this, of the hydrogen bonds. But it'll also stick to more hydrogen and even sodium. It's not only water it sticks to, other covalent compounds also. And those bonds are fairly easily broken. They're not. Everything DNA has wrapped around like a spiral ladder, has the bases hooked to each other. Those hydrogen bonds. And you got to unzip the DNA to make a copy of it. Did you know that? You have to unzip it like a zipper. And the hydrogen bonds are easily unzipped by enzyme that's produced. Because those hydrogen bonds, though they do hold the DNA together, are not superglue. They can be undone, and also they can be redone. So you can unzip the DNA to two strands, make you a copy, and then re-zip it like it was and send your copy off somewhere. The body does it all, and we have a section coming of lesson where you're going to see that being done. I got some things off of YouTube that has some very good animations, better than I can ever do myself. So these hydrogen bonds are pretty important. And I just mentioned DNA, and I didn't know it was coming, but here it is. I tell you about the DNA molecule being held by bonds, but, you know, all a protein is a bunch of amino acids hooked together like a pearl necklace. It's just one after another. And the question is, what hooks one acid to the next acid? To the next acid? They're hydrogen bonds. Hydrogen bonds are used throughout nature to hook things together. And when you remove, if I got two amino acids right here, and I remove water from them, they would then stick together with the water. Now to make them separate, I got to put the water back and separate. When you eat steak or salmon or whatever meat you eat, you know, you cut it up and you chew it up and you swallow it. Now in your stomach, those bonds are starting to be broken because you can't use that steak, but you can use those amino acids because that steak is from a cow. And the acids are arranged to make a cow. So when you eat that steak, you break down to the acids. You can then rearrange the acids into human protein. And that's how we grow. You know, football players, I know Hardaway, they have big old steak dinners. And what steak build?
Protein.
Muscles. Why? Muscles are proteins. That steak from the cow you ate, that's the cow's muscles. But that's cow muscle. I need human muscle. It's the same amino acids though. The amino acids that make the cow muscle will make our muscle if you rearrange it. So you digest that steak from the cow. And then our body rearranges those acids and our muscles get bigger and stronger. Now we have taken, it's the same building blocks. I mean, letters of the alphabet, you rearrange and make new words, don't you? That's how the body does it. And if you get eaten by a shark, then the shark will take your meats, reduce it down to amino acids, restructure them, and make shark muscle. Acids never change, just from one to another. I mean, they've been here for eons. It's just that's called conservation of mass. You don't make new ones, you just rearrange them. If you stop eating, will you keep growing? No, you need to continual input of food, nutrients, so you'll heal yourself when you're damaged. You'll grow to maturity. And just to walk around, you need energy. Protein. You ever hear the term denatured?
Yes.
Denatured alcohol. If you take meat and you cook it, it will get easier to tear apart. Ever seen rugs that just pull apart in hand? Before it's done, though, it won't pull apart. And what you're doing, the heat destroys the shape of the protein. When you take in French fries into your mouth, your salivary glands make an enzyme called amylase. Amylase will not break down meat, will not break down fat, but will break down carbohydrate like French fries. But the problem is, though, you swallow it before it gets finished breaking the French fry down. That French fry then goes to your stomach. Now, your mouth adheres around 7, water is 7 on the pH scale. You get below 7, you're an acid. Above 7, you're a what?
Basic.
You're a base. Well, your stomach historically is an acid or base?
Acid.
Strong acid. Strong acid. Amylase works in a pH of 7. When it gets to a pH of 2, it will stop working. Because the enzyme is made of protein. And the pH changes the shape of the protein. It can no longer digest. Now, but the beauty is, inside your stomach, that French fry, nothing's happening to it. Because the stomach breaks down meats. Now, when the stomach content enters the intestines, then the pancreas makes some more amylase to finish doing what the mouth started. The pancreas also makes lipase, which attacks lipids. It produces the proteases, which break down proteins. As a matter of fact, the pancreas has a juice that can dissolve any kind of food you've eaten. Intestines only can digest carbohydrates. The stomach only digests protein. So if you start to lose your pancreas, you're in dire straits. Real bad shape. All right. Let me see if I can, I'm going to time call it quiz. I'm looking ahead. They're all hydrogen bonds, aren't they? Well, let's do them, see, we're going to still have a test, aren't we? We're right here, right?
Yeah.
Yes, ma'am.
So they say that you can only break down around 20 grams, is it, per day of
Say again?
protein? 20 grams a day protein
Yeah.
is what normally we can break down.
But it depends on what your metabolism is. Babies have a higher metabolism with it. Baby's heart.
So if we took a digestive enzyme, like
Was it?
as a supplement,
Digestive enzymes would help you break down food if you don't have enzymes yourself.
right? So if we took that in addition to like a dietary supplement, would we be able to break down more protein than
You
20?
would break down more, you sure would.
Just remember those are electrons.
And if you were to lose your pancreas through cancer, then it will give you enzymes through insertions. Because you don't, we can give it artificial, you can still eat your food, but we got to help you out by giving you enzymes that the pancreas won't give you that you lost. Can you live without your stomach? Yeah, we can take a slap out of you. But then you got to watch out what you eat, because then you lost the ability to break down fat. To break down meats. That's like give you trypsin as an enzyme for breaking down. If I gave you those enzymes, then you can get by. But those are expensive things. And a lot of folks who lose their stomach because of maybe stomach cancer, they're not long for the world. You know why, don't you? When you've infected that big an organ,
All the others.
it is somewhere else, I guarantee you.
Or some
It's
diseases.
somewhere else. It's somewhere else. If you can catch it early on before it spreads, you can stop cancer. But most of us don't do anything like cancer until it hurts. And we stop hurting because it spread, and then the death sentence is signed for it. All cancers, every cancer in the world is completely curable in its first stages. But it don't hurt you until when? To the later stages. And most folks don't go to a doctor when you're feeling all right. You go when you're hurting. And they ask you, how long you had that lump right there? Oh, I saw it about 2 years ago. Just coming in? Well, I was busy. I had to go to school and I had babies to raise. And nothing's worth your life, is it? But a lot of folks don't go. I ain't got the money. I ain't got the insurance. I ain't got the time. And then a doctor sees you when you're in the worst condition possible, and you get mad because of misdiagnosis. They never saw you when you're well, did you? You don't know how you are when you're all right. Give them something to compare you back to. I always go to, when I have a new doctor, I go to the doctor when I'm healthy. Take a look at me now, while things are fine. So when I get sick, you got something to compare it back to. Otherwise, you tie her hands behind her back. My doctor is Jill Moore. I taught her in high school. And she was good. So I don't have, she called me Mr. Teff. I said, call me Bobby. She said, no, Mr. Teff. I'm Mr. Teff. I said, all right. I call her Doc. I said, hey, Doc. But she's as nice as can be. And a lot of folks say, you got a lady doctor? I said, no, I have a doctor. Who is a lady? They're not two kind of doctors, right? In man's mind, there are, though. There are doctors and then there are female doctors. That's wrong.
That's true.
I mean, you think that way.
A doctor.
Ladies don't mind going to a male doctor, do you?
No.
Do you mind going to a female doctor?
I would kind of mind.
Had you really go to a male doctor? Ladies, had you prefer a man or a woman doctor?
Woman. It depends
Woman?
on what it is.
It's culturally based.
Huh?
It's cultural.
It is called, you're exactly right.
Like,
But most men will prefer to go to a male doctor.
Like my husband wouldn't let me have a male gynecologist. I won't.
Alright, so we're stopping right here. I'm making note to start number
You can have a
17 tomorrow.
It's not a
We will finish this thing tomorrow.
Oh, somebody-